On one side, we have the dialectical reasoning of 2nd century Eastern philosophy. On the other, the strict matrix topology of modern non-associative algebra. The foundational text connecting them is the Mula Madhyamaka Karika, or MMK, composed by Nāgārjuna around 150 CE. This text functions as a systematic phenomenological falsification program. Nāgārjuna's primary target is a concept called svabhāva. This is the assumption that a phenomenon possesses intrinsic, context-independent existence, that it exists from its own side, regardless of its relationship to other things. We are exploring the hypothesis that this analytical program shares a specific structural architecture with an E₈ CFT framework. If the phenomenological dialectic and the mathematical topology of exceptional algebras are mapping the same relational invariants, the implications for our understanding of reality are significant. To test this, we will model the algebraic conditions svabhāva and map the 4 modes of the causal tetralemma to the behavior of Sedinonian zero divisors. The proof is restricted to the framework's E₈ boundary scale of 51.9 GeV and its genus 10 grid geometry. This model operates with 0 free parameters. There's no room for arbitrary mathematical tuning to force a correspondence with the philosophy. This is a study of structural equivalence. While Nāgārjuna used phenomenological analysis and modern physics uses matrix algebra, the objective is to determine if both arrive at the same relational map. If the results align without the need for adjusted parameters, it suggests an independent mathematical derivation of Madhyamaka's core invariants. In this framework, we define a generic physical observable as a measurable element within a mathematical space. To possess svabhāva, an observable's identity must remain invariant regardless of its measurement context. As shown in definition 2.1, this requirement for context-independent identity maps precisely to the property of associativity across any 3 operators. If the result of evaluating observable A remains unchanged regardless of the order in which operators B and C are applied, intrinsic existence is algebraically preserved. We now place this requirement within the exceptional Jordan algebra, the specific space governing observables in this model. If the exceptional Jordan algebra is non-associative, the conditions for svabhāva cannot exist within this space. Theorem MI establishes that any generic non-scalar observable resides in the off-diagonal entries of the matrix. These off-diagonal entries are governed by the rules of octanonian multiplication, represented here by the phanoplane. To test for associativity, we construct a triple by isolating 3 distinct imaginary octanonian units. These units define our variables A, B, and C as traceless Hermitian elements within the algebra. Step 1 of the computation yields the product of B times A times C within the first entry. Step 2 calculates the opposing product, B times C times A. When we substitute the octonian parameters, the 2 results are not equal. The evaluation returns a non-zero value. The Jordan associator is non-zero. The observables inherit the inherent non-associativity of the octonians. This non-zero value, the associator norm, quantifies the observable's reliance on its specific measurement context. This mathematical measure of divergence from associativity aligns with the relational structure Nāgārjuna identified as pratitya samutpada, or dependent origination. This structural analysis applies to the causal tetralemma in MMK Chapter 1, the fourfold refutation of how things arise. Testing these causal modes requires a shift in the mathematics. At the octonian level, we are in a division algebra where interactions do not result in 0. We move up to the Sedinians. This level contains a 14-dimensional geometric manifold where the division property fails. This manifold contains the zero divisor ideal, a state where 2 non-zero elements multiply to exactly 0. This Sedinonic extension provides the algebraic mechanism necessary to test for the collapse of causal relationships. We evaluate causal transfer between x and y as an algebraic norm product. Mode 1 is self-causation. Requiring the cause and effect to be the same restricts the interaction to a smaller associative subring of the algebra. This restriction makes self-causation insufficient to describe the behavior of the full non-associative observable space. Mode 2 is other causation. If the cause and effect are entirely distinct, they occupy orthogonal pure sectors in the matrix. Multiplying elements from orthogonal sectors triggers the zero divisor ideal. The product vanishes, meaning no causal transfer occurs. Mode 3 posits causation from both self and other. This is modeled as a linear combination of the two previous variables. Due to Peirce grading, the other component becomes causally inert. The equation reduces back to mode 1. Within this mapping, every traditional mode of causation either reduces to a trivial substate or annihilates. The algebra indicates that svabhāva-bearing causation is structurally impossible. These falsifications lead to the ultimate theorem of Madhyamaka, śūnyatā, or emptiness. Emptiness represents a state of conditional balance. It describes a phenomenon that is empty of intrinsic nature because it arises dependently. In our exceptional algebra, this state corresponds to the vanishing trace equation, where the sum of the diagonal elements is 0. When all dependently originated forms are summed across the matrix, the total equals 0. Here, emptiness is the precise algebraic balance of the system. The dialectical arguments in LMK chapters 1 and 15 find a structural match in the behavior of exceptional Jordan algebras and setanonic zero divisors. This mapping is achieved with zero free parameters. Nāgārjuna mapped phenomenological relational invariants. Modern physics derives algebraic relational invariants. Despite the different methods and time periods, both frameworks isolate the same constraints on the nature of reality. The ancient philosophy and the quantum algebra observe the same underlying geometry: 3 routes, 1 mountain.